Yeah, let's consider isotope effect on mass spectrometry more in detail. Okay, um, as I said, now finding molecular mass and structure by mass spectrometry is important, but depending on ionization method, the patterns uh, spectrum becomes different. With electron ionization, often no molecular peak is observed. Fragmentation occurs severely, but these fragments provide clues to the structure of an unknown. Okay? With chemical ionization, protonated molecular peak MH plus is usually observed. Okay, don't forget there's a proton. Proton is there. Well, there is a nitrogen rule. Nitrogen, organic compound often contains one or more nitrogen atoms. Okay, but nitrogen, atomic number is 7, and depending on the number of nitrogen atoms, okay, so the molecular ion peak may be in a odd number or even number. Okay, let's look at the nitrogen rule. If a compound has an odd number of nitrogen atoms, okay, in addition to any number of carbon, hydrogen, halogens, oxygen, sulfur, silicon, and phosphate, then has an odd nominal mass. Okay, odd number. There's 1, 3, 5, like that. Okay, and for a compound with an even number of nitrogen atoms, 0, 2, 4, like that, has an even nominal mass. All right. Molecular ion at mass to charge ratio 128. Okay, let's see. You obtained this molecular peak. Okay, molecular ion peak can have 0, no nitrogen, or maybe 2 nitrogen atoms. Okay, maybe 4. You may say 4 nitrogen atoms, but too many. Okay, um, not only nitrogen but also carbon and hydrogen atoms must be there. Maybe 1 or 2 nitrogen atoms are there, but it cannot have 1 nitrogen atom. Okay, that's the nitrogen rule. And now examine molecular ion and isotope patterns. Okay. Electron ionization of aromatic compounds. Aromatic compound so are those containing benzene rings. Okay, so these aromatic compounds are very stable. Okay, so with even electron ionization method, usually you can get significant intensity for molecular ion peak here. Okay, um, so this one molecular ion peak is the base peak, most intense, and we set this peak height 100%. Okay, 100. So this is the uh, base peak in the spectra of benzene and biphenyl. Yeah, biphenyl is also classified as aromatic compounds. Okay, because it has two benzene rings put together. Okay, and let's look at the there's a mass spectrum mass spectrum. Okay. And what is the molecular mass of benzene? C6H6. Okay, it's a 78. Okay, 78. So this one molecular mass mass to charge ratio at 78. The peak is the highest. Okay, that's the base peak, and also it is benzene. Okay, a molecular peak, right? And and other small peaks below this number, and they are all fragmentation peaks. Okay? But you see at molecular charge mass to charge ratio at 79, you see about 6.5% of this peak. Okay, this amount, yeah, this intensity cannot be ignored. Okay, and you may wonder what that is. Okay? Likewise, biphenyl has many, fragmentation peaks with 100% molecular peak. Okay, and also on the right hand side, 12.9% of this molecular peak, this peak appears, and also even at 156 there is a small peak. Okay, what are they? And these peaks, what are they? At the beginning of this chapter, I mentioned that atomic mass or molecular mass, we consider all the isotope effects. Okay, in other words, when you take some amount of atoms or molecules, inevitably there are uh, isotopes. Okay, because the particle number of particles are too many. Okay, so and also the distribution of isotopes are all uniform, yeah, all over the world. Yeah. But in mass spectrometry, since the detector differentiate each mass, right? So you see, inevitably you see these peaks, okay, and we know very easily, yeah, they are due to the isotope, okay. That is called isotope effect, okay. And let's identify what this one, n plus 1 peak, what are they? And also n plus 2 peak, what are they? Okay. And benzene and biphenyl, yeah, these simple compounds consisted of only hydrogen and carbon. Yeah? And hydrogen, this ordinary hydrogen atom, its abundance is quite high, 99.988%. But there is another hydrogen, yeah, this is deuterium. Yeah? In Korean, 중수소. Okay, its mass number is 2 because it contains, the nucleus has one proton and one neutron. So its nominal mass is 2. It takes 0.012%. Of course, there is, a triton, okay, 삼중수소, but its concentration is extremely small. Okay, so we don't have to be concerned about that. Okay, here, yeah? And also for carbon, most abundant carbon is mass number 12. It takes 98.93%. But there is another carbon 13. It takes 1.07%. Yeah, they are the natural abundance. Okay. Of course, there is a carbon 14. Yeah, mass number 14. That's a radioactive carbon. Okay. You know, our Earth, there is in a cosmic ray from outside, okay, outside the space, and then that hits nitrogen, mass number 14, and very small portion of nitrogen becomes carbon 14. Okay, that's the radioactive carbon, and depending on the concentration of the radioactive carbon, you can date the age of living things. Okay, yeah, that is so famous carbon dating method. Anyway, but now let's consider only these isotopes. Okay, that's a natural abundance, and this abundance is uniform all over the world. Okay, and here, uh, why you ask why it takes a 6.5% of this one with respect to this molecular peak. Yeah, this is 100%. Okay, and this is the equation to calculate this peak's intensity. Okay, let's assume one compound is only composed of carbon and hydrogen atoms and n carbons and m hydrogen atoms. Okay, and here we consider this isotope effect. Okay, for n plus 1 peak, intensity is given by this equation. N is the number of carbons, and multiplied by 1.08%. But here, you may ask why. Professor, carbon 13 takes 1.07%. Okay, but don't be confused because we, the molecular peak, we put this molecular peak 100%. So if you set this number to 100% and proportionally this 1.07% becomes 1.08%. Okay, that's why. And also we have to also consider this hydrogen isotope, deuterium. Okay, whose mass number is 2 and its abundance is 0.012%. Okay, but since this ordinary carbon takes almost 100%, although you divide by let's see 0.012 divided by 0.99988, still you get 0.012%. Okay, yeah, this is intensity. Yeah, here is the calculation for benzene. Okay, let's calculate the percentage of this n plus 1 peak. Okay, this is mass number 79 and there are 6 carbon atoms, 6 times 1.08 plus 6 carbon atoms and then 6 hydrogen atoms, 6 times 0.012, and then we get 6.55%. Okay, but this is almost 6.5% identical. Okay, yeah, as we expected. What about this bipenyl? Okay, bipenyl, the uh, it is carbon 12, hydrogen 10. Okay, and 12 times 1.08 plus 10 times 0.012. Okay, it is 13.1%, but here is 12.9%. Well, there's just a small discrepancy. Yeah, that is acceptable. Okay, you um, so you now what these peaks are and how you calculate the abundance. Okay, this is a percentage. Okay, this table shows all kinds of isotopes. Okay, of selected elements. Yeah. Other than that, virtually every element in the periodic table, there are more than 100 elements, but each element, virtually each element has one or more isotopes. Okay, for example, let me see, hydrogen here. Okay, hydrogen has two isotopes whose mass numbers are 1 and 2. For borons, also 2 carbons, also 1 and 2, mass number 12 and 13. For nitrogen, also 2, mass number 14 and 15. Okay, and also this oxygen, there are 3 isotopes. Okay, mass number 16, 17, 18. All right, and this 16 is the most abundant species, and mass number 18 also we cannot ignore, and but mass number 17 takes some portion, although small. Yeah, like that. Okay. Yeah. And this table 2 shows the isotope abundance factors in percent, okay, for interpreting mass spectra. Okay? It is not difficult to derive these equations. Okay, for hydrogen element, you know, one, you know, the x plus one peak. Okay, this is what there is a nominal peak plus only one mass added, right? What's the abundance? Since hydrogen, I'm sorry, hydrogen has only two isotopes. This is a base peak. Okay, let's we put this peak to 100%, and uh, the other isotope is also only the mass number 2. Okay, so the equation is that simply we multiply the number of hydrogen atoms times 0.012. Okay, but what about the carbon? Okay, carbon, uh, it is, look at that, carbon mass number 12 and 13. Okay, there are 12 and 13. For 12 or 13, it takes, let me see, 1.07%. But as I said, if you put this number to 100% and this one 1.07 becomes 1.08. Okay, that's why here 1.08. Yeah, but what about this one? Yeah, why we have to consider the two additional mass, okay, relative to the nominal mass. Why equation is given like that? Okay, now here and I explained in detail. Now from table 1, this mass number abundance is like that. I already expected. X plus 1 abundance is what? Since we set this percentage to 100%, okay, we adjust also this abundance with respect to 100%, okay, and then it becomes 1.08 times n, number of carbon atoms. Okay, yeah, you see, if but x2, x plus 2 abundance, what does that mean? Let's see. You have many carbon atoms, n carbon atoms in the uh, molecule, okay, and there is a chance that two arbitrary two carbon atoms mass uh, is 13, okay, at the same time. All right, although the probability is quite low, anyway there is a chance, yeah, to have x plus 2 peak. Okay, so we have to do it statistically. Okay, so for the x plus 2 this mass abundance, so we have to take arbitrarily 2 carbon atoms out of n atoms. Okay, so in this case we put here n combination 2 times 100% divided by 98.98 times what? 1.07. Okay, also we multiply by this one again because we took we take 2 carbon atoms, okay, 1 and 2, and then you will get this number. Okay, exactly here. Okay, likewise you can derive other the abundance factor for for example for silicon. Okay, you can do the this kind of calculation to get this equation. Okay, yeah. This is not difficult. Okay? All right. Yeah, here is an example. Yeah? Listening to a mass spectrum. Okay. Let's read this example. In the chemical ionization mass spectrum of pentobarbital, okay, pentobarbital. So in your textbook, you can see the structure. Yeah? The peak with the most significant intensity at the high end of the mass spectrum at mass to charge ratio 227. Okay, let me show you. Yeah, this one, pentobarbital. Okay, the problem says chemical ionization is also employed, and here this one, this is not a base peak, but this is looks like a molecular peak. Yeah, but since we employed chemical ionization, this peak contains proton. Okay, so mass number increased by 1. Okay, to 27, not to 26. Okay. uh, this number is suspected to be MH plus. Okay, this is good suspicion. Okay, if this is so, then the nominal mass of M, this pentobarbital, is 226. Okay, the nitrogen rule tells us. Yeah, now we apply nitrogen rule. Since this mass number is even, and then there must be even numbers of nitrogen atoms. Okay, even mass must have an even number of nitrogen atoms. If you know from elemental analysis that the compound contains only carbon, hydrogen, nitrogen, and oxygen. Okay, how many atoms of carbon would you suspect are in the molecule? Okay, yeah, this is a good example. Okay, uh, yeah, let's look at the solution. The mass to charge ratio 228 peak has 12%. Okay, here, I'm sorry, I skipped. Okay, here, look at that. This one, it's a small peak. Yeah, this is mass number 228. Yeah, this is because of an isotope effect. Okay, isotope effect, and then this percentage here, if you look at the this percentage relative abundance, I don't know, maybe around 10% or so. uh, it's a 12%. Okay, here, yeah, of height of mass. Oh, 227 with respect to this although this is not a base peak, if we take this one as a molecular peak and set 100%, actually the mass number 228 is a little bit below 10%, but with respect to this peak, it takes this 228 peak has 12%. Okay, and the table 2 tells us that n carbon atoms will contribute, okay, n times 1.08% intensity at mass to charge 228 from carbon 13. Okay, but now we simply ignore the contributions from this one, deuterium, yeah, deuteron, okay, the 중수소, and oxygen 17, because their abundance is quite small. Okay, this is only 0.012%. You know, deuterium, and oxygen 17 is 0.038%, quite small. Yeah. So now we only consider carbon. Okay, carbon atoms. Nitrogen, mass number 15, nitrogen makes a larger contribution, but there are probably few atoms of nitrogen in the compound. Okay, let's see. this nitrogen contribution cannot be ignored. Okay, here nitrogen mass 15 takes 0.368%, but uh, simply we assume there are not many nitrogen atoms in the compound. You know, most abundant element in the compound is hydrogen and carbon. Okay, so our first guess, yeah, this is just the first guess. Number of carbon atoms is what? Observed peak intensity for n plus 1 divided by contribution per carbon atom. Okay, must be equal to uh, this one. N plus 1 peak 228 is 12%. 12 divided by carbon atom contribution, which is 1.08. Okay, yeah, and it gives 11.1, approximately 11. So we can uh, assume the number of carbon atoms in this peculiar compound is 11. Okay, the actual combination composition of M plus MH plus at this mass number is what? Carbon 11, hydrogen 19, oxygen 3, and 2. Okay, so using the table 2, theoretical intensity of this one, this peak is what? Intensity. We all consider the contributions of every element in the compound. Okay, from carbon, 11 times 1.08. Okay, from hydrogen, mass number 2, 19. It has 19 hydrogen atoms times 10 0.012, plus from oxygen 17, 3 times 3 oxygen atoms there, this one, and then there are 2 nitrogen atoms. Okay, here, and it gives 13.0%. Okay, uh, so we have from the spectrum, this is actual value 12%, but now we calculate it is 13%. The radical intensity is within 10% uncertainty. Okay, the uncertainty is small, within 10%. Yeah? So this calculation makes sense. Okay, yeah, this way, yeah, we can uh, calculate the carbon atoms by some with some assumptions. Okay, yeah, but this kind of calculation, not all the time hold. Okay, so we need more information here. So yeah, at least we have to know the number of elements. Okay, each element in the compound, right? Okay, let's stop here.